have explored our primary trig functions, which I'll remind you, sine of theta is equal to opposite over hypotenuse, cosine of theta is equal to adjacent over hypotenuse, tangent of theta is equal to opposite over adjacent. It's now time to introduce the new set of trig functions, the inverse trig functions. Mathematically, you can write it as follows. Arc sin x arc cos x and arctan x. Now x is just an input to this function, so it's just a number that you put in. You can also write it like this. This one for sine, for cosine looks like this, and for tangent it looks like this. Now I'd like to warn you that this looks like you're raising sine to the -1 power, which would turn it to 1 over sine x. It really isn't. This is just how they write it mathematically for arc sine, arc cos, and arc tan. If it confuses you, don't use this notation. Just use arc sine, arc cos, and arc tan. But technically, they all mean the same thing. Okay, so these trig functions are inversely related to our normal trig functions, sine, cosine, and tangent. But what does this exactly mean? Well, to understand, let's look at an inverse operation you already seen before. So we have squaring something and square rooting something. So squaring something is just saying, what is this number times itself? Square rooting is asking, what times itself is equal to this number, which is x. These two functions are opposites, but mathematically, we would call them inverses. And the reason why they're inverses is because if you apply these functions to one another, they would cancel each other out. For example, if we did the square root of x squared, we would just get x. And likewise, if we did the square root of x, all of it squared, we would get x. These two functions essentially cancel each other out. Now this is very similar to our inverse trig functions. Remember our primary trig functions. Let's use sine as an example. If we give it an angle, then it will give us an output that shows the ratio of the sides. In this case, it would just be the opposite over the hypotenuse. So you can kind of say that sine is kind of like a machine where if you give it an angle, it will give you a ratio. The inverse means the opposite of that function. So if we reversed it, this time, instead of giving it an angle, in order for arc sine to work, we give it a ratio, and this thing will give us an angle. Remember that the ratio has to be opposite over hypotenuse. Essentially, what the inverse functions do is that if you give them a ratio, they give you an angle. Now this is the exact opposite of what the sine function does. And it's especially useful for finding angles you don't know if you already know the ratio. So let's do a question to show what I'm talking about. So sine of theta is equal to 0.5. Now this is just saying sine of what angle is equal to 0.5. And a reminder that this 0.5 is the opposite to the hypotenuse. Let's solve for it. Now we want to get rid of this sine over here, so we need to cancel it out somehow. And we know that the inverse of sine is arc sine. So we can apply arc sine on both sides. Now if you remember, arc sine and sine are inverses, so they cancel each other out. And we end up getting theta is equal to arc sine of 0.5. How do you solve for these arc sines and arc cosines and arc tangents? Well, just look on your calculator. Usually, they have the inverse functions already on. So in this case, we want arc sine of 0.5. So sine, this inverse sine, 0.5, and we end up getting our answer. Theta is equal to 30. Alright, let's practice solving onto our calculator. So, sine of theta is equal to 1, so let's inverse sine both sides. So, these signs cancel out, and we end up getting theta is equal to the inverse sine of 90 degrees. Alright, let's do the same for the cosine. So for here, we take the inverse cosine on both sides. These two cancel out, and we end up getting theta is equal to inverse cosine of 0.5. And this ends up being 60 degrees. Finally, let's do the same thing with the tangent. So apply the inverse tangent on both sides. These two cancel out, and we end up getting theta is equal to inverse tangent of 1, and that is equal to 45 degrees. Alright, now let's use our understanding of these new inverse functions to solve for missing angles for triangles. So, the first step is to write an equation using the trig function that describes the ratio given. Next, you would inverse both sides of the equation and then solve for the missing side. So, I'd like to remind you, sine of theta is equal to opposite over hypotenuse, cosine of theta is equal to adjacent over hypotenuse, tangent of theta is equal to opposite over adjacent. So, let's solve. So we can see that the opposite here, because that's opposite to the angle, the opposite is equal to 4, and the hypotenuse, because that's the longest side, is equal to 6. Do we have a ratio that is the opposite to the hypotenuse? Oh, it's sine. So we can write sine of theta is equal to 4 over 6. Alright, now let's just inverse sine both sides. Equals to the inverse sine of 4 over 6, and these two signs cancel each other out, and we get theta is equal to the inverse sine of 4 over 6. And if you put that into your calculator, you will get approximately 41.81 degrees. Remember, it's in degrees because it spits out a angle, not a ratio. Also, we use the approximate sign because we're rounding off here. Okay, let's do the next question. Now we can see that because this side is next to the angle, it makes that the adjacent. And the longest side is right here, so therefore it is the hypotenuse. Okay. Do we have a ratio that describes the adjacent to the hypotenuse? Oh, it's cosine. So you can write cosine of theta is equal to 7 over 10. Then we inverse cos both sides. Inverse cos of 7 over 10. These two cosines cancel each other out, and we end up getting theta is equal to the inverse cos of 7 over 10. And this is 45.57 degrees. So theta is approximately this much. Okay, and let's do one more. So since this one's the opposite to the angle, 4 is equal to the opposite, and since this side is right next to it, the angle, it is the adjacent. Do we have a ratio that describes the opposite to the adjacent? Oh, it's tangent. So we can write tangent of theta is equal to the opposite over the adjacent. Inverse tan both sides. inverse tan both sides. The inverse tangent and the tangent cancel out, and we get theta is equal to the inverse tangent of 4 over 7. Put that into your calculator, and we get theta is approximately 29.74 degrees. So, for summary, the inverse trig functions undo the trig functions. These inverse functions are the opposite of normal trig functions, which means if you give them a ratio, they give you an angle. So contrary to normal ones, where you give them an angle and they spit out a ratio, this time if you give them a ratio, they'll give you an angle. When you inverse both sides, you're applying the function to both sides, much like square rooting both sides or squaring both sides. You're not adding, subtracting, or dividing the function. So if you have sine of theta is equal to 0.75, then you do the inverse sine on both sides. You're not dividing or multiplying by sine, you're just applying this to both sides. So don't mix that up. And these cancel out. That's why we're able to get theta by itself when we do the inverse sine. I hope this helped for understanding inverse functions. As always, you can always email me if you have any questions. And this is Low Academy signing off.